Dinosaurs are a lie. Not the kind of lie where someone made them up. Not a conspiracy. Something stranger. Something that will keep you awake tonight. I've spent 40 years studying the fossil record, and the more I learn, the more one question haunts me. How did these creatures exist at all? The oxygen levels required to sustain them? The atmospheric pressure needed for pterosaurs to fly? The cardiovascular engineering necessary to pump blood up a 40-foot neck? The thermal regulation required to keep an 80-ton body from cooking itself? Every single variable had to be perfect. Not approximately right, perfect. 1 degree warmer, they overheat. 1% less oxygen, they suffocate. Slightly different gravity, their bones shatter. A marginally different atmosphere, flight becomes impossible. I've run the numbers. The probability of all these conditions aligning simultaneously for 165 million years is essentially zero. And yet, here I am, holding a fossil that shouldn't exist. The dinosaurs weren't just improbable, they were impossible. And by the end of this video, you'll understand why their existence might be the greatest mystery science has never solved. I want you to do something right now. Take a breath, a deep one. Feel your chest expand. Feel the air fill your lungs. Notice how effortless it is. You've done this 20,000 times today without thinking about it. That breath you just took contains 21% oxygen. The rest is mostly nitrogen with traces of carbon dioxide, argon and other gases. This ratio has remained relatively stable for millions of years. It's what your body evolved to process. It's what every mammal on Earth is calibrated to breathe. Now I want you to imagine something different. Imagine that breath contained 35% oxygen, nearly double what you're used to. Your first reaction might be that this sounds wonderful. More oxygen means more energy, right? Your cells would be supercharged. You'd feel incredible. And you would, for about 30 seconds. Then you'd start to notice problems. Your heart would race uncontrollably. The oxygen would begin to damage your cell membranes. Free radicals would flood your system, destroying tissue faster than your body could repair it. Within hours, you'll be experiencing oxygen toxicity, confusion, seizures. Death would follow shortly. Human beings cannot survive in high oxygen environments for extended periods. Our biology isn't built for it. We evolved in a 21% oxygen world, and that's where we belong. But the dinosaurs didn't live in our world. The Mesozoic era, the age of dinosaurs, existed in an atmospheric composition so different from today that it might as well have been another planet. And here's where the first impossibility emerges. For dinosaurs to exist, particularly the giants, they required oxygen levels significantly higher than what we breathe today. Estimates vary, but most paleoclimatologists agree that oxygen concentrations during peak dinosaur periods reached somewhere between 25 and 35%. This wasn't a minor fluctuation. This was a fundamentally different atmosphere. Let me explain why this matters. Consider the Argentinosaurus. This titanosaur stretched over 100 feet long and weighed approximately 80 tons. To put that in perspective, that's the weight of 14 African elephants combined into a single animal. Now think about the physics of such a creature. When you scale up any animal, you encounter a fundamental problem that engineers call the square-cube law. If you double the length of an animal, you quadruple its surface area, but you multiply its volume, and therefore its weight, by 8. This creates cascading problems. Bones have to support more weight, but bone strength doesn't scale proportionally. Muscles have to work harder, but muscle power doesn't increase fast enough. And most critically, lungs have to supply oxygen to a much larger body, but lung capacity can't keep pace with oxygen demand. This is why elephants are essentially the maximum size for modern land mammals. Any bigger, and the biology breaks down. The lungs can't supply enough oxygen. The heart can't pump blood fast enough. The animal overheats because it can't radiate body heat efficiently. The dinosaurs shattered this limit. They grew to sizes that should be physically impossible for air-breathing land animals. How? The conventional explanation is that they had more oxygen to work with. Higher atmospheric oxygen meant each breath delivered more fuel to the cells. Combined with their highly efficient avian-style respiratory system, featuring one-way airflow rather than our tidal in-out breathing, dinosaurs could theoretically support much larger bodies than mammals can. This sounds reasonable. It's the explanation you'll find in most textbooks. But there's a problem nobody talks about. High oxygen atmospheres are inherently unstable. And by unstable, I mean explosively dangerous. Do you know why hospitals are so careful about oxygen tanks? Why there are strict no-smoking signs everywhere near supplemental oxygen? Because oxygen is an accelerant. It doesn't burn itself, but it makes everything else burn faster, hotter, and more violently. In a 21% oxygen atmosphere, a forest fire is dangerous. In a 35% oxygen atmosphere, a forest fire becomes an apocalyptic inferno. The flames spread faster. The temperatures burn hotter. Wet wood burns. Green vegetation burns. Things that shouldn't catch fire become explosive. And the Mesozoic era had plenty of ignition sources. Lightning struck constantly, just as it does today. Volcanic activity was intense throughout the dinosaur age. Meteorite impacts, while rare, occurred regularly over geological time. Sparks from rock falls, spontaneous combustion from decomposing vegetation. In a high oxygen world, any of these ignition sources should have triggered continent-spanning firestorms, not ordinary forest fires. Biblical conflagrations that would have sterilized entire land masses. The geological record shows evidence of fires during the dinosaur age. Charcoal deposits exist, but they don't show what should be there. They don't show the kind of megafires that physics predicts should have occurred regularly in a high oxygen atmosphere. Something doesn't add up. The dinosaurs needed high oxygen to exist. But high oxygen should have made their world a perpetual inferno. Yet somehow, for 165 million years, the fires stayed contained enough for complex ecosystems to thrive. Some scientists propose that high humidity levels suppressed fire spread. The Mesozoic was a greenhouse world, hot and wet. Water vapor in the air could have acted as a fire suppressant. But this creates another problem. High humidity makes heat intolerable for large animals. This is why you feel so miserable on a hot, muggy day. Your body cools itself through sweat evaporation. When the air is already saturated with moisture, evaporation slows down. Your internal temperature rises, you overheat. An 80-ton animal generates enormous amounts of metabolic heat. Even standing still, its internal processes produce energy that needs to be dumped into the environment. In a hot, humid atmosphere, that heat has nowhere to go. The dinosaurs should have cooked themselves, and yet they didn't. Something allowed them to survive in conditions that thermodynamics says should have killed them. Let me introduce you to another problem with the Mesozoic atmosphere. For flying reptiles, the pterosaurs, the physics become even more problematic. Quetzalcoatlus had a wingspan of approximately 36 feet. It stood as tall as a giraffe when on the ground. Estimates of its weight vary, but most fall between 400 and 500 pounds. This animal flew. Let me be clear about what that means. We're talking about something the size of a small aircraft, made of flesh and bone, that could launch itself into the air, fly for hundreds of miles, and land again safely. Modern engineers will tell you this shouldn't work. When you scale up a flying animal, weight increases faster than lift. The wings have to grow proportionally larger, but they also have to be proportionally stronger to support themselves. At some point, you hit a limit where wings large enough to generate sufficient lift would be too heavy to flap. For the weight of Quetzalcoatlus, that limit should have been reached and exceeded. The animal should not have been able to fly. One proposed solution is that the Mesozoic atmosphere was denser than today's. More gas molecules in the same volume of space would provide more lift per square foot of wing surface. A Quetzalcoatlus in a denser atmosphere might have been able to fly when it couldn't in modern air. But atmospheric density depends on two factors: the weight of the gases and the total atmospheric pressure. If the atmosphere had the same pressure as today, but different composition, the density wouldn't change enough to matter. Higher oxygen levels alone don't significantly change density because oxygen molecules aren't much heavier than nitrogen molecules. For the atmosphere to be significantly denser, the total pressure would have to be higher. And there's a problem with this. High atmospheric pressure causes nitrogen narcosis. It's what deep-sea divers experience when they go too deep. The increased pressure forces more nitrogen into the blood, where it acts as an anesthetic. Confusion, impaired judgment, eventually unconsciousness and death. The dinosaurs couldn't have functioned in a high-pressure atmosphere any more than we can. Their brains would have been affected. Their neural processes would have been impaired. So we have an impossible situation. The dinosaurs needed high oxygen to grow large. But high oxygen should have caused perpetual firestorms. Flying reptiles needed a denser atmosphere to achieve lift. But higher pressure would have poisoned them. Giant bodies needed some way to dump heat. But the humid conditions that suppressed fires would have prevented heat dissipation. Every solution creates new problems. Every explanation raises new questions. And we haven't even gotten to the strangest part yet. The high oxygen atmosphere of the Mesozoic didn't just appear, it had to be created. And the process that created it was itself highly improbable. Atmospheric oxygen comes from photosynthesis. Plants absorb carbon dioxide, use sunlight to split the molecules, and release oxygen as a waste product. The more plants, the more oxygen. But plants also consume oxygen when they die and decompose. Bacteria break down dead vegetation, and this process uses up oxygen. Under normal circumstances, these two processes balance out. Oxygen levels remain stable. For oxygen to accumulate to the levels needed for dinosaurs, something unusual had to happen. Dead plants had to stop decomposing. During the Carboniferous period, before the dinosaurs evolved, this actually occurred. The plants of that era, giant ferns and primitive trees, developed a new structural molecule called lignin. This was the woody material that allowed them to grow tall, but nothing had evolved yet to digest lignin. When these plants died, they didn't rot. They just accumulated, piled up, compressed over millions of years into what we now call coal. All that undecomposed carbon was locked away. The oxygen that would have been consumed in decomposition remained in the atmosphere. Levels rose to perhaps 35%. But then fungi evolved the ability to break down lignin. Dead wood started rotting again, the oxygen surplus began to decline. The dinosaurs evolved during a narrow window when oxygen was still high enough to support giants, but low enough that the world wasn't constantly on fire. This window lasted about 165 million years, which sounds like a long time, but is actually a remarkably precise slice of Earth's 4.5 billion year history. Before that window, oxygen was too high. The fire risk was too great. Complex land ecosystems couldn't develop. After that window, oxygen dropped to modern levels. Giant body plans became impossible. The age of dinosaurs ended. The timing had to be exact. Too early, and they would have burned. Too late, and they would have suffocated. And here's what keeps me awake at night. We have no good explanation for why that window existed when it did, for as long as it did. We have no good explanation for why the fires stayed contained. We have no good explanation for how flying reptiles achieved lift in an atmosphere that physics says shouldn't have supported them. The dinosaurs needed an atmosphere that shouldn't have existed, configured in a way that shouldn't have been stable, for a duration that shouldn't have been possible. And yet, here are the fossils. I hold them in my hands. I run my fingers over bones that are 65 million years old. I trace the shapes of creatures that defy everything I understand about biology and physics and chemistry. They existed. That's undeniable. The evidence is right here. But how? This is only the first impossibility. The atmosphere was just the beginning. Because even if we accept the miracle of the air they breathed, we still have to explain the planet they walked on. And that's where things get truly strange. I need to tell you about something that happened to me in 1987. I was in Montana at a dig site in the Hell Creek Formation. This is one of the richest dinosaur fossil beds in the world. The last chapter of the dinosaur story is written in these rocks. We had been excavating for weeks. The summer heat was brutal. The work was tedious. And then, on an ordinary Tuesday afternoon, I found something that changed how I think about everything. It was a footprint. Not a fossil bone, a footprint, preserved in what had once been mud at the edge of an ancient river. The print was enormous, nearly a metre across. The three-toed impression of a large theropod, probably a relative of Tyrannosaurus. You could see where the mud had squished up between the toes. You could see the texture of the skin. You could see exactly where this animal had stepped 67 million years ago. I knelt there in the dust, and I put my hand inside that print. And I felt something I can only describe as vertigo. This wasn't an abstraction anymore. This wasn't a skeleton in a museum. This was a moment, a specific instant when a living creature walked across wet earth and left a mark. That animal was real. It stood right here. It looked out at a landscape I would never see, and I realized, kneeling in that ancient mud, that I had no idea how any of this was possible. Not the animal, the mud, the river, the whole planet. Let me explain. When that theropod walked across that riverbank, the continents were in completely different positions than they are today. North America was not where you see it on modern maps. The Atlantic Ocean was narrower, the Pacific was wider. The entire configuration of land and sea was fundamentally different. This matters more than most people realize. The positions of the continents determine everything about Earth's climate. They determine where ocean currents flow. They determine where rain falls. They determine which regions are habitable and which are deserts. They determine the distribution of heat from the equator to the poles. Change the continental configuration, and you change the entire planetary system. During the age of dinosaurs, the continents were arranged in a way that created the most stable, most uniformly warm, most life-friendly climate in Earth's history. This wasn't an accident. It couldn't have been an accident. The mathematics of it are too precise. Let me walk you through it. At the beginning of the Mesozoic era, about 250 million years ago, all the continents were fused together into a single supercontinent called Pangaea. This sounds like it should be good for life. One big landmass means animals can walk anywhere, right? Wrong. Pangaea was a disaster. Think about how weather works. Water evaporates from the ocean, forms clouds, and falls as rain on land. But clouds can only travel so far before they dump their moisture. The interior of Pangaea was thousands of miles from any ocean. Rain couldn't reach it. The center of the supercontinent was one of the most hostile environments in Earth's history. Temperatures swung between extremes, searing hot during the day, freezing at night. No water, no vegetation. Nothing but rock and dust and death. Life clung to the coastal margins. The interior was uninhabitable. For dinosaurs to flourish, Pangaea had to break apart. The continents had to separate and drift to positions where ocean moisture could reach every landmass. The great deserts had to shrink. The habitable zone had to expand. This process began about 200 million years ago. Pangaea started to rift. Cracks appeared. Seas flooded into the gaps. The supercontinent began to fragment. But here's the first impossible thing. Continental drift is driven by processes deep in the Earth's mantle. Convection currents in the molten rock push the plates around. These processes are chaotic. They're influenced by temperature variations, compositional differences, the weight of the crust, and countless other factors. There's no reason, no physical mechanism that would cause the continents to drift into positions optimal for life. The mantle doesn't know or care whether the surface is habitable. It's just moving rock around, and yet that's exactly what happened. As Pangaea broke apart, the fragments drifted to positions that created ideal climate conditions, not just acceptable conditions, optimal conditions. The Atlantic Ocean opened gradually, allowing ocean currents to circulate heat around the planet. The continents arranged themselves in a pattern that minimized polar ice and maximized greenhouse warming. The great interior deserts shrank and eventually disappeared. By the height of the dinosaur age, the Cretaceous period, Earth had no ice caps. The poles were temperate. Forests grew in Antarctica. Crocodiles lived above the Arctic Circle. The entire planet was a garden. This is not normal. For most of Earth's history, the planet has had significant climate variations between the equator and the poles. Ice ages have come and gone. Deserts have expanded and contracted. Climate stability is the exception, not the rule. But for 165 million years, during exactly the period when dinosaurs dominated, the climate remained remarkably stable and uniformly warm. The probability of this happening by chance is essentially zero. Let me give you a specific example. During the Cretaceous period, North America was split in half by a shallow sea. This was the Western Interior Seaway, a body of water that extended from the Gulf of Mexico to the Arctic Ocean, cutting the continent into two separate landmasses. This seaway was critical for the dinosaurs that lived in western North America, including Tyrannosaurus and Triceratops. It moderated the climate, bringing moisture inland and preventing the extreme temperature swings that had characterized the continental interior during Pangaea. But the seaway required a very specific set of conditions to exist. First, the sea level had to be high enough to flood the continental interior. This required warm global temperatures, which caused thermal expansion of the oceans and prevented water from being locked up in ice caps. Second, the continent itself had to be configured correctly. The tectonic forces building the Rocky Mountains were simultaneously causing the continental interior to subside, creating a basin that could hold water. Third, the ocean currents had to flow in patterns that brought warm water from the Gulf into this basin, keeping it from becoming a stagnant swamp. All of these conditions had to align simultaneously. Change any one of them, and the seaway doesn't exist. Without the seaway, the interior climate becomes harsh. Without a mild interior climate, the great dinosaurs of Western North America can't survive. And this is just one continent. Similar stories played out on every landmass. In South America, the separation from Africa created isolated ecosystems where unique lineages evolved. The titanosaurs, the largest land animals ever, developed in South America. They couldn't have evolved anywhere else. The specific conditions of that isolated continent, the particular plants that grew there, the particular climate patterns were necessary for their development. In what is now India, a landmass moving northward across the Indian Ocean created an island laboratory where strange endemic forms developed. The dinosaurs of India were unlike those anywhere else on Earth. In Australia, early separation from the southern landmasses allowed marsupial-like mammals to gain a foothold while dinosaurs still ruled. This set the stage for Australia's unique fauna after the dinosaurs disappeared. Every continent was configured just right. Every ocean current flowed in the right direction. Every climate zone developed in the right place. The planet was arranged like a laboratory, like someone had set up an experiment to see how large life could get under optimal conditions. But wait, I need to tell you about something even stranger. The continental positions didn't just determine climate, they determined something else that was critical for dinosaur survival: volcanism. The movement of tectonic plates creates volcanoes. Where plates collide, rock melts and erupts. Where plates pull apart, magma rises to fill the gap. Volcanic activity is an inevitable consequence of continental drift. And volcanoes were essential for the dinosaurs. Here's why. Over geological time, carbon dioxide is gradually removed from the atmosphere by chemical weathering. Rain dissolves CO2 and carries it into the ocean, where it eventually becomes limestone. Without a mechanism to return this carbon to the air, CO2 levels would steadily decline. The greenhouse effect would weaken. The planet would cool. Volcanoes are that mechanism. They release CO2 back into the atmosphere, maintaining the greenhouse effect, keeping the planet warm. During the age of dinosaurs, volcanic activity was precisely calibrated to maintain optimal temperatures. Not too much, which would have caused runaway warming. Not too little, which would have allowed the planet to cool. How precisely calibrated? The sun was actually dimmer during the Mesozoic than it is today. Solar output increases gradually over billions of years. During the dinosaur age, the sun provided about 98% of the energy it provides now. This should have made Earth colder, but it wasn't colder, it was warmer. The volcanic CO2 output exactly compensated for the reduced solar input. The greenhouse effect was strengthened by just the right amount to maintain warm temperatures worldwide. This is a balancing act of incredible precision. The sun's output was fixed by nuclear physics. The volcanic activity was determined by plate tectonics. These are independent systems. There's no feedback mechanism that would cause them to balance. And yet they balanced. For 165 million years. I want you to think about what that means. Imagine you're playing a game where you have to keep a ball balanced on a board, but you're wearing a blindfold, and someone keeps changing the tilt of the board randomly, and you're not allowed to touch the ball directly. That's what Earth was doing during the dinosaur age. Maintaining climate stability through two independent systems that had no way of communicating with each other. It shouldn't have worked. The probability of it working for 1 million years would be remarkably low. For it to work for 165 million years is, statistically speaking, impossible. And we're still not done with the impossibilities, because even with the perfect atmosphere and the perfect continental configuration and the perfect climate balance, the dinosaurs still faced another challenge: food. Those giant bodies required enormous amounts of energy. An Argentinosaurus needed to consume over 1,000 pounds of vegetation every day. A T-Rex needed hundreds of pounds of meat. The planet had to produce enough biological productivity to feed these giants, not just in one location, but everywhere dinosaurs lived. Not just for one generation, but for millions of years. This required the right plants, the right prey animals, the right ecosystem structure, the right energy flow from sun to vegetation to herbivores to carnivores. The food chain had to be configured perfectly. Every link had to be in place. And here's the remarkable thing: it was. For the entire age of dinosaurs, global biological productivity was among the highest in Earth's history. The planet was a greenhouse overflowing with life. Food was abundant everywhere. When I stand in the Montana Badlands and look at those Hell Creek fossils, I'm not just seeing individual animals, I'm seeing the end product of a planet-sized life support system. A system that maintained optimal conditions across every variable, in every location, for longer than mammals have even existed. The dinosaurs didn't just live on Earth, they lived on a version of Earth that was specifically configured to support them. And I don't know how that happened. I've spent my career looking for natural explanations. I believe in natural explanations. The scientific method has served us well for centuries. But when I look at the evidence, when I really look at all the factors that had to align for dinosaurs to exist, I find myself confronting something that feels less like random chance and more like design. Not intelligent design in the religious sense. I'm not making a theological argument. But design in the sense of configuration, arrangement, setup. The planet was arranged to support dinosaurs. The atmosphere was configured to enable their biology. The climate was tuned to optimize their success. How did this happen? I don't know. And that uncertainty keeps me up at night. Because if we don't understand how the conditions for dinosaurs arose, we don't really understand anything about why Earth has the history it does. We tell stories about natural selection and random mutation and survival of the fittest. These are true stories as far as they go. But they assume a backdrop. They assume an environment. They assume a stage on which evolution can perform. Someone built that stage. Something configured it, and I don't know what. The footprint I found in 1987 is still there, preserved in the rock. I've visited it many times over the years. I put my hand in the same depression and try to imagine the animal that made it. And every time I feel the same vertigo. Not because the dinosaur is strange, because the world that made the dinosaur possible is strange, because the whole planet had to be aligned just right for that creature to exist. The dinosaur was walking on ground that shouldn't have been there, breathing air that shouldn't have existed, under a sun that should have been too dim to keep the planet warm. Everything was impossible. And yet, there's the footprint. Let me tell you about the tallest animal that ever lived, Sauroposeidon. The name means earthquake god lizard. It stood about 60 feet tall. Its neck alone was nearly 40 feet long. If it stood next to a 6-story building, it could look over the roof. Now, I want you to think about the blood in that animal's body. Blood is heavy. It weighs about 8 pounds per gallon. A large sauropod might have had over 500 gallons of blood in its body. That's 2 tons of fluid that had to be moved constantly through a system of vessels against gravity to every cell of that enormous body. And here's the problem. To push blood up a 40-foot neck, you need pressure, enormous pressure. The heart has to generate enough force to overcome gravity, overcome the resistance of the blood vessels, and still deliver blood at a useful pressure to the brain. Let's do the math. Blood pressure is measured in millimeters of mercury. Your blood pressure is probably around 120/80. That's the pressure your heart generates to push blood around your 5 or 6 foot body. For every foot of additional height, you need roughly 25 more millimeters of mercury of pressure. A Sauroposeidon, with a head 40 feet above its heart, would need around 1,000 additional millimeters just to overcome gravity. Add in the resistance of the blood vessels, and you're looking at a heart generating pressures of 1,200 to 1,500 millimeters of mercury. That's 10 times human blood pressure. Now think about what that means for the blood vessels. Your arteries are designed to handle pressures around 120. At much higher pressures, they would rupture. The walls would simply tear apart from the stress. Sauroposeidon's arteries had to handle 10 times that pressure without rupturing. This requires blood vessel walls of extraordinary thickness and strength. But thick blood vessel walls are heavy, and they don't stretch well, and they require more energy to maintain. But wait, the problem gets worse. What happens when Sauroposeidon lowers its head to drink water? All that blood, pressurized to reach the top of a 40-foot neck, suddenly has gravity working with it instead of against it. The pressure at the brain doesn't just stay the same, it spikes. Imagine turning on a garden hose and then suddenly lowering the end 40 feet. The water doesn't just trickle out, it blasts. The pressure at the low end increases dramatically. When Sauroposeidon lowered its head, blood should have rushed into its brain with enough force to blow out every vessel. The animal should have suffered a catastrophic stroke every time it took a drink. This is not speculation. This is physics. This is how fluids work in gravitational fields. There's no getting around it. And yet, Sauroposeidon existed. It drank water. It didn't die every time it leaned down. How? We don't fully know. Some scientists propose that sauropods had valves in their neck arteries that could slam shut when the head lowered, preventing blood from rushing downward. This would be similar to the valves that giraffes have, but far more elaborate. Others suggest that the blood vessel structure in sauropod brains was different from ours. Perhaps smaller vessels with more branching, creating more resistance, limiting how fast blood could enter the skull. Still others propose that sauropods had a completely different arrangement of their circulatory system. Perhaps multiple hearts distributed along the neck. Perhaps separate circulatory systems for different body regions. All of these are hypotheses. We can't test them directly because soft tissue doesn't fossilize. All we have are bones. The cardiovascular system that made those bones possible is gone forever. But whatever the solution was, it had to work perfectly. A partial solution, a system that mostly worked, would have resulted in dead sauropods. Natural selection doesn't give points for almost surviving. The engineering had to be complete, and it had to evolve from smaller ancestors that didn't need such elaborate systems. How do you evolve your way to a solution you don't need yet? How do you develop valves in your neck before your neck is long enough to require them? This is the paradox of evolutionary engineering. The final system makes sense, the intermediate steps don't. But cardiovascular engineering is just the beginning. Let me tell you about sauropod breathing. You breathe by moving air in and out of your lungs. This is called tidal ventilation. Air comes in, gas exchange happens, air goes out. The same path, just reversed. This system works fine for animals our size, but it has a fundamental limitation. At any given moment, much of the air in your respiratory system is dead air. It's been used. The oxygen has been extracted. The carbon dioxide has been dumped. But it's still sitting in your trachea and bronchi, mixing with fresh air, reducing efficiency. For a small animal, this doesn't matter much. The dead air volume is small relative to the lung volume. But as animals get larger, the dead air problem grows. Consider a sauropod with a 40-foot neck. That neck is basically a giant tube connecting the head to the body. Every time the animal breathes, air has to travel 40 feet down that tube to reach the lungs, and then 40 feet back up to exit. The volume of air in that neck tube is enormous. Hundreds of gallons, perhaps. All of it dead air, all of it mixing with fresh air, all of it reducing respiratory efficiency. If sauropods had breathed like mammals, they would have suffocated. Their lungs would have been filled mostly with stale air. They couldn't have extracted enough oxygen to survive, let alone to power their massive bodies. But sauropods didn't suffocate. They thrived for over 100 million years. The solution was the avian respiratory system. Birds don't breathe like mammals. Air flows through their lungs in one direction only. Fresh air enters, passes across the gas exchange surfaces, and exits without ever reversing course. There's no mixing of fresh and stale air. Every breath is maximally efficient. Sauropods inherited this system from their theropod ancestors. We can see evidence of it in their bones. Those hollow bones we marvel at in museums weren't empty. They were filled with air sacs that were part of the respiratory system. When a sauropod inhaled, air didn't just go to the lungs. It flowed into a complex system of air sacs distributed throughout the body, even extending into the bones. When the animal exhaled, that stored air flowed through the lungs, providing a continuous supply of fresh oxygen. The long neck wasn't a liability. It was part of the respiratory system. Air storage along its length actually enhanced efficiency rather than hindering it. This is elegant engineering. It's beautiful, actually. A system that turns what should be a fatal flaw into an advantage. But here's what bothers me. This system had to exist before the long necks evolved. You can't develop a 40-foot neck and then figure out how to breathe. You have to have the breathing system first. The ancestral dinosaurs that eventually gave rise to sauropods were small. They didn't need elaborate air sac systems. Their simple necks worked fine with basic respiratory arrangements. So why did they have the foundation for a system they didn't need? Evolution is supposed to work by small, incremental changes, each providing a survival advantage. You don't evolve features for future use. Natural selection operates on present conditions, not anticipated future requirements. And yet, the respiratory system that allowed giant sauropods to exist was present in their ancestors long before it was necessary. It's as if the blueprint was there, waiting. Let me give you another example. Sauropod bones are extraordinary structures. They're not solid like mammal bones. They're filled with air pockets and internal struts, like the inside of a bird's wing bone. This makes them remarkably light for their strength. An 80-ton animal with solid bones would collapse under its own weight. The bones would shatter. But the hollow, strutted structure of sauropod bones distributed weight efficiently, allowing sizes that should have been structurally impossible. Engineers recognize this design principle. It's used in bridges, in aircraft, in buildings. Hollow structures with internal bracing are stronger per unit weight than solid structures. But sauropod bones weren't designed by engineers. They evolved over millions of years through random mutation and natural selection. Here's my question. How do you get from solid bone to this incredibly sophisticated structure through small incremental changes? Each intermediate step has to be viable. An animal with half-developed hollow bones, with some internal struts but not others, would be weaker than either solid or fully hollow bone. It would be selected against. It should have been eliminated. Yet somehow this transition occurred. Somehow the intermediate steps survived, despite being theoretically disadvantaged. I'm not arguing against evolution. Evolution clearly happened. The fossil record shows the transitions. The genetic evidence confirms common descent. But the mechanism, the step-by-step process that turns small, solid-boned reptiles into giant, airborne sauropods, isn't as straightforward as textbooks suggest. Let me tell you about one more impossibility before we move on. Sauropod necks weren't just long, they were mobile. These animals could sweep their heads across wide arcs, reaching vegetation at different heights and distances without moving their bodies. This required joints, connections between the vertebrae that allowed rotation, extension, and lateral movement. And each of those joints had to remain stable under enormous loads. Consider the forces involved. A sauropod head might have weighed 1,000 pounds. The neck might have weighed 20,000 more. When the animal extended its neck horizontally, all that weight was supported by the vertebral joints at the base of the neck. The torque was astronomical. Imagine holding a 20,000-pound weight at arm's length. Now imagine doing it all day. Now imagine doing it while moving, while walking, while dealing with wind loads. The joints between sauropod vertebrae were engineering marvels. They had to be strong enough to support massive weights, flexible enough to allow movement, durable enough to last for decades without wearing out. Mammal joints can't do this. If you try to scale up a mammal's spine to sauropod proportions, the joints fail. The cartilage wears through. The bones grind against each other. The animal is crippled by arthritis within years. Sauropod joints were different. They had pneumatic elements, cushioned by air rather than just cartilage. They had bone structures that distributed force across wide areas rather than concentrating it at points. They had growth patterns that continually repaired wear damage. Every aspect of sauropod anatomy tells the same story. Problems that should have been fatal were solved by engineering innovations that shouldn't have been possible through incremental evolution. I've studied these animals for decades. I've held their bones in my hands. I've measured their dimensions and calculated the forces involved. And the more I learn, the more I find myself confronting the same uncomfortable question. How? How did evolution, working through random mutation and natural selection, arrive at solutions that seem designed? How did systems that required multiple simultaneous changes, each useless without the others, emerge through a process that can only make one change at a time? I don't have good answers. I can describe what existed. I can show you the fossils. I can explain the physics of how these animals functioned. But I cannot explain how they got there. The path from small ancestral forms to the giants of the Mesozoic passes through territory that shouldn't be traversable. The dinosaurs weren't just large animals. They were solutions to engineering problems. Each species was an answer to a question about how biology could be pushed further than it should go. And the most impossible thing about them isn't any individual feature. It's that all these features had to exist together, in the same animals, at the same time, on a planet configured perfectly to support them. The atmosphere, the climate, the continental positions, the cardiovascular system, the respiratory system, the skeletal structure. Take away any one of these, and the dinosaurs become impossible. All of them had to be in place. All of them had to work for 165 million years. That's not evolution. That's a conspiracy of circumstances so vast and so precise that it defies probability. And yet, here I am, looking at bones that prove it happened. I need to tell you about the most impossible dinosaur of all. Technically, it wasn't a dinosaur. Pterosaurs were a separate lineage of reptiles, cousins to the dinosaurs rather than dinosaurs themselves. But they lived alongside the dinosaurs, shared their world, and disappeared with them at the end of the Cretaceous. And they did something that physics says shouldn't work. They flew. I'm not talking about gliding. Lots of animals can glide. Flying squirrels glide. Sugar gliders glide. Even some snakes can flatten their bodies and glide between trees. Gliding is just controlled falling. You jump from a high place and use your body surface to slow your descent and move horizontally. It requires no special adaptations beyond a large surface area to catch air. Flying is different. Flying means generating lift. Flying means staying airborne without losing altitude. Flying means taking off from the ground and climbing into the sky. For an animal to fly, it needs wings that can push air downward faster than gravity pulls the animal downward. This requires power, enormous power relative to body weight. Small animals can fly fairly easily. A sparrow weighs about an ounce. Its flight muscles can easily generate enough power to lift that weight. But as animals get larger, the physics become punishing. Weight increases with the cube of linear dimensions. Double an animal's length and you multiply its weight by 8. Lift increases with the square of wing dimensions. Double the wingspan and you only multiply lift by 4. See the problem? Make a flying animal bigger and weight increases faster than the ability to support it. At some size, the wings simply can't generate enough lift to get airborne. For birds, this limit seems to be around 40 pounds. The largest flying birds today, like the wandering albatross, weigh about 25 pounds and have wingspans around 11 feet. There have been some larger flying birds in the past, perhaps up to 70 or 80 pounds. But pterosaurs blew past this limit like it didn't exist. Quetzalcoatlus northropi had a wingspan of approximately 36 feet. Estimates of its weight vary, but most fall between 400 and 500 pounds. That's 5 to 10 times heavier than the largest flying birds ever. The animal stood as tall as a giraffe when on the ground. Its head was nearly 10 feet long, mostly beak. When it spread its wings, it blocked out the sun. And it flew. We know it flew because we've found its fossils on multiple continents. It couldn't have walked between them. It couldn't have swum. It had to cross oceans. A 500-pound flying animal. Let that sink in. Modern aeronautical engineers will tell you this shouldn't work. The power required to keep 500 pounds airborne would exceed anything biological muscles can generate. The wing loading, the weight supported per square foot of wing surface, would be too high for sustained flight. And yet, Quetzalcoatlus existed for millions of years. Let me tell you what we think we know about how it was possible. First, the bones. Pterosaur bones weren't just hollow. They were incredibly thin-walled and reinforced with internal struts. They were engineering marvels, maximizing strength while minimizing weight. A Quetzalcoatlus skeleton might have weighed only about 60 pounds, despite the animal's size. Second, the wing membrane. Unlike a bat's wing, which is relatively thick skin, or a bird's wing, which is covered with feathers, a pterosaur's wing was an incredibly thin, taut membrane stretched over a single elongated finger bone. This membrane was packed with muscle fibers that could actively change its shape, adjusting aerodynamic properties in real time. Third, the air sacs. Like their dinosaur cousins, pterosaurs had an air sac respiratory system. This not only made breathing more efficient, but also reduced body density. The animal was, in a sense, partially inflated. All of these adaptations push the weight down and the lift up. They move the line between possible and impossible flight, but they didn't move it enough. Even with all the weight-saving measures, even with the most efficient wing design, 500 pounds is still 500 pounds. Gravity still pulls at the same rate. Air still provides resistance at the same density. I've run the calculations many times. I've consulted with aerospace engineers. The consensus is always the same. Quetzalcoatlus shouldn't have been able to take off. The problem isn't staying airborne. Once aloft, the animal could probably soar efficiently using thermals and updrafts. It could glide for enormous distances, much like an albatross. The problem is launch. Birds take off by jumping with their legs while flapping with their wings. The legs provide initial altitude, while the wings provide forward thrust and lift. This works well for small birds, but it doesn't scale. A 500-pound animal can't jump very high. Its legs would have to be massively muscled to achieve any altitude at all. And those muscles would add weight, which would require more jumping power, which would require more muscles. It's a vicious cycle. At some point, legs strong enough to launch a flying animal become too heavy for that animal to fly. Quetzalcoatlus seems to have solved this with a completely different launch mechanism. Based on trackway fossils and biomechanical analysis, scientists now believe that pterosaurs used a quad launch. Instead of jumping with their back legs while flapping with their front wings, they used all four limbs simultaneously. The animal would crouch down, gathering energy in its massive flight muscles, which were anchored to its forelimbs. Then it would push off with both arms and both legs at once, vaulting into the air with explosive force. Computer simulations suggest this could work. A quad launch generates more power than a bipedal jump, potentially enough to get 500 pounds airborne. But here's what bothers me. This launch mechanism requires an incredibly specific arrangement of muscles, bones, and joints. The arms have to be strong enough to support the initial push. The shoulders have to be structured to handle the force. The coordination has to be perfect, and this system had to evolve before the animals got large enough to need it. Small pterosaurs could take off with simple bipedal jumps. They didn't need a quad launch. So why would they develop one? The answer, presumably, is that the proto-quad launch provided some advantage even for small pterosaurs. Maybe it allowed faster takeoffs. Maybe it worked better from awkward surfaces. But this feels like a just-so story. It's an explanation that works backward from the result to imagine a plausible path. It doesn't tell us that path actually happened. And there's another problem. Pterosaurs evolved flight independently from birds and bats. 3 separate lineages developed powered flight from non-flying ancestors. 3 times, the impossible problem of generating lift was solved. Each time, the solution was different. Birds have feathered wings powered by complex chest muscles. Bats have membrane wings stretched between elongated fingers. Pterosaurs had membrane wings supported by a single hyper-elongated finger. 3 different solutions to the same impossible problem. Now, you might say this proves that flight isn't really impossible. If evolution found 3 different ways to achieve it, it must not be that hard. But consider what each solution required. Birds needed to evolve feathers, which are incredibly complex structures. They needed hollow bones, air sacs, specialized flight muscles, keeled sternums for muscle attachment, and numerous other adaptations. All of these had to develop in the right order, each step providing some advantage, eventually combining into a working flight system. Bats needed to elongate multiple fingers, develop a wing membrane between them, evolve echolocation to navigate in the dark, modify their metabolism for the energy demands of flight, and more. Pterosaurs needed their own suite of unique adaptations. Each of these evolutionary paths required hundreds of coordinated changes. Each change had to be beneficial in itself, or at least not harmful, while also contributing to the eventual ability to fly. The odds against any one of these paths succeeding are astronomically small. The odds against all 3 succeeding are essentially impossible. And yet, all 3 happened on the same planet. During overlapping time periods, flight evolved 3 times on Earth. That's 3 separate miracles. 3 impossible events. But let me tell you about something even more impossible. Pterosaurs didn't just fly. The largest ones hunted on the ground. Remember Quetzalcoatlus? Standing as tall as a giraffe, with a head nearly 10 feet long? This animal didn't just soar majestically overhead. When it landed, it walked. And when it walked, it hunted. We used to think giant pterosaurs were like giant pelicans, skimming fish from the water. Their long beaks seemed designed for aquatic feeding. But recent analysis has changed that view. The neck structure of Quetzalcoatlus wasn't flexible like a heron's. It was stiff. The animal couldn't have darted its head quickly to catch fish. The legs were strong and well adapted for walking. The trackways we found show a competent terrestrial stride. The beak wasn't shaped for scooping fish. It was shaped for stabbing. Current thinking is that Quetzalcoatlus was an apex predator on land. It would fly to a hunting ground, land, fold its wings against its body, and walk through the environment like a demonic giraffe. When it encountered prey, small dinosaurs, mammals, lizards, whatever it could catch, it would stab downward with that massive beak. Then it would tilt its head back and swallow the prey whole. This is an animal that could fly across oceans and then hunt like a land predator. An animal that was equally at home in the sky and stalking through the undergrowth. An animal that combined two completely different survival strategies in a single body. The engineering required to make this work is staggering. The wings had to fold compactly enough to walk without dragging. The legs had to support the full body weight during terrestrial hunting. The muscles had to switch between flight mode and walking mode efficiently. And the whole system had to be light enough to fly, but strong enough to catch and kill prey. Every requirement conflicts with the others. Light conflicts with strong. Flight adapted conflicts with walking adapted. Aerial hunter conflicts with terrestrial hunter. And yet Quetzalcoatlus resolved all these conflicts. It was a flying giraffe demon that should have been impossible 10 different ways, but existed anyway. I want to tell you one more thing about pterosaur impossibility. Pterosaur wings were membrane, skin, essentially, stretched over bones. Unlike feathers, which are dead structures that can be replaced, pterosaur wing membrane was living tissue. If a bird damages its wing feathers, it can still fly while they regrow. A torn feather heals naturally over time. If a pterosaur tore its wing membrane, it would bleed. The tear would spread. The animal would be grounded, probably permanently. Think about what this means for a flying animal. Every flight is a risk. A collision with a branch, a talon wound from a predator, an awkward landing could end the animal's flying career forever. Death would follow shortly, since a grounded pterosaur couldn't effectively hunt or escape predators. Pterosaurs were flying on wings made of vulnerability, and yet they dominated the skies for over 150 million years, from tiny insectivores to giants that dwarfed any bird that ever lived. Through changing climates, shifting continents, and mass extinctions. They should have been too fragile to persist. They should have been too large to fly. They should have been too awkward on the ground to hunt. They shouldn't have existed. But I have their bones in my museum. I can touch them. I can measure them. I can verify that they were real. The pterosaurs existed. The physics said no. Biology said it was possible anyway. How do you make sense of that? How do you integrate impossibility into your worldview? I don't have an answer. After 40 years, I don't have an answer. All I have are the fossils, the impossible fossils of impossible creatures from an impossible world. I want to talk about time. Not time as you experience it, with days and weeks and years slipping past. I want to talk about deep time, geological time, time measured in millions and hundreds of millions of years. The dinosaurs ruled for 165 million years. That number is almost impossible to comprehend. Let me try to put it in perspective. Modern humans have existed for about 300,000 years. If you compressed all of human history into a single day, from midnight to midnight, the dinosaurs ruled for 1,550 such days. More than 4 years of human equivalent time. The Roman Empire lasted about 500 years. If the Roman Empire were 1 inch on a timeline, the dinosaur era would be 27 feet long. The entire history of civilization, from the first cities in Mesopotamia to this moment you're watching this video, is about 10,000 years. The dinosaurs ruled for 16,500 times as long. You cannot imagine this duration. Your brain isn't built for it. The human mind evolved to handle timescales of days, seasons, lifetimes. Deep time is simply beyond our cognitive capacity. But here's why this matters for the impossibility of dinosaurs. For 165 million years, the conditions we've discussed had to remain stable. The oxygen levels, the atmospheric pressure, the continental configuration, the climate balance, the volcanic activity, the ecosystem productivity. Change any of these variables significantly and the dinosaurs would have died. Not evolved differently, not adapted, died. Large animals are vulnerable to environmental change. They need lots of food, they have long generation times. They can't evolve quickly enough to track rapid environmental shifts. And environments always shift. This is the fundamental nature of Earth's systems. Climates change, continents move, sea levels rise and fall, ice ages come and go. Volcanic episodes poison the atmosphere. Asteroid impacts reset ecosystems. The Earth is not stable. It never has been. And yet, for 165 million years, conditions remained stable enough for the dinosaurs to thrive. Let me tell you about some of the things that should have killed them, but didn't. First, the eruption of the Ontong-Java Plateau. About 120 million years ago, in the middle of the Cretaceous period, a massive volcanic province erupted in what is now the Pacific Ocean. This was one of the largest volcanic events in the last 250 million years. The lava flows covered an area the size of Alaska. The gases released would have caused significant climate disruption, warming, acidification, oxygen depletion in the oceans. Marine ecosystems were affected. We see evidence of extinctions and disruptions in the fossil record. But the dinosaurs kept right on going. They barely noticed. Somehow, the conditions on land remained within the bounds that dinosaurs needed. The climate didn't swing too far. The oxygen didn't drop too much. The ecosystem productivity didn't crash. Second, the opening of the Atlantic Ocean. Throughout the Mesozoic, the Atlantic was widening. This wasn't a gradual, smooth process. It happened in pulses, as magma erupted along the mid-Atlantic ridge and pushed the continents apart. Each pulse released enormous amounts of carbon dioxide. Each pulse warmed the climate. Each pulse should have disrupted the delicate balance that the dinosaurs needed. But the balance held. The climate warmed somewhat, yes, but it didn't warm catastrophically. It remained within the range that the dinosaurs could tolerate. Third, fluctuations in sea level. During the dinosaur era, sea levels rose and fell by hundreds of feet. At times, shallow seas covered much of what is now dry land. At other times, the continental shelves were exposed. These fluctuations should have been devastating for coastal ecosystems. The dinosaurs that lived near the sea should have faced constant habitat destruction. But the record shows remarkable resilience. Dinosaur populations adapted, moved, survived. The disruptions that should have caused extinctions instead just caused relocations. Fourth, changes in vegetation. The Cretaceous period saw one of the most significant events in plant evolution, the rise of flowering plants. Before the Cretaceous, the land was dominated by ferns, conifers, and other non-flowering plants. The dinosaurs had evolved to eat these plants. Their digestive systems were adapted to process this vegetation. Then, relatively rapidly, flowering plants began to take over. They offered new food sources, but also new challenges, different nutritional content, different growth patterns, different ecosystem dynamics. A shift, this fundamental, should have caused extinctions among specialized herbivores. And we do see some turnover in the fossil record. But the dinosaurs as a group adapted, they kept thriving. I could go on. There were climate excursions, volcanic episodes, tectonic events, and evolutionary shifts throughout the age of dinosaurs. Every one of them should have posed existential threats to large, slow-reproducing, specialized animals. And every one of them somehow failed to eliminate the dinosaurs. How? The standard explanation is that the dinosaurs were just well adapted. They had efficient respiratory systems, flexible behavior, diverse diets. They could handle environmental variation. But this explanation doesn't satisfy me. It's not that dinosaurs were tough, it's that the challenges they faced were conveniently just below the threshold of lethality. Think about that. For 165 million years, every volcanic eruption, every climate shift, every ecological disruption was just barely survivable, strong enough to cause stress. Not quite strong enough to cause extinction. What are the odds of that? The Earth doesn't calibrate its catastrophes. Volcanic eruptions don't check whether the animals can handle them before they happen. Climate shifts don't moderate themselves to allow survival. These are random processes, chaotic systems that produce unpredictable outputs. And yet, for 165 million years, the random outputs just happen to fall within survivable ranges. Let me give you an analogy. Imagine you're playing Russian roulette. One bullet in a 6-chamber revolver. Each trigger pull has a 1 in 6 chance of killing you. If you survive one pull, that's plausible. 5 out of 6 times, you'll survive. If you survive 10 pulls, that's getting remarkable. The odds are about 16%. If you survive 100 pulls, that's essentially impossible. The probability is so low, it might as well be 0. The dinosaurs pulled the trigger thousands of times over their 165 million year reign. Volcanic events, climate shifts, tectonic disruptions, each one a potential bullet. They survived them all. Until they didn't. And that brings me to the strangest part of the dinosaur story. After surviving everything the Earth could throw at them for 165 million years, they were killed by a single event. One asteroid impact, one bad day. Done. Doesn't that strike you as odd? Creatures tough enough to survive 100 million years of environmental chaos were killed instantly by a single catastrophe. It's as if they were allowed to exist until they weren't. As if permission was granted and then revoked. I know how that sounds. It sounds like I'm implying design or intention. I'm not making that claim. What I'm pointing out is that the pattern doesn't fit our usual understanding of how evolution and extinction work. Normally, species become more vulnerable over time. They specialize. They occupy narrower niches. They become dependent on specific conditions. When those conditions change, they die. The dinosaurs did the opposite. They became more diverse over time. They occupied more niches. They spread to every continent. They adapted to environments from tropical forests to polar regions. They should have been getting more resistant to extinction, not less. And yet, at the end, they were wiped out almost completely. Only the birds survived. Something about this picture doesn't add up. Let me tell you about the end of the Cretaceous. The asteroid that killed the dinosaurs was about 6 miles wide. It struck what is now the Yucatan Peninsula of Mexico at about 40,000 miles per hour. The impact released energy equivalent to billions of nuclear bombs. The immediate effects were catastrophic. Everything within hundreds of miles was vaporized instantly. A wave of superhot air spread across North America, igniting fires. Tsunamis hundreds of feet tall swept across the Gulf of Mexico. But the immediate effects weren't what killed the dinosaurs. The global effects were the impact threw billions of tons of debris into the atmosphere. This debris blocked sunlight. For months, perhaps years, the Earth was dark. Photosynthesis stopped. Plants died. Herbivores starved. Carnivores starved. At the same time, sulfur from the vaporized bedrock combined with water vapor to form sulfuric acid. Acid rain fell across the planet, poisoning freshwater sources and acidifying the oceans. The global food chain collapsed. Everything that depended on the sun, which is everything, died, except for a few survivors. Small animals that could hide underground. Animals that could eat detritus and decay. Animals that could survive for extended periods without food. Birds made it through. They were small. They could eat seeds that had been preserved in the soil. They could hide in burrows. Mammals made it through. Same reasons. Small bodies, flexible diets, ability to take shelter. Crocodilians made it through. They could slow their metabolism to almost nothing and wait out the darkness. But the large dinosaurs, the ones we think of when we say the word dinosaur, were gone. Every single one. The 100-foot sauropods, the 10-ton tyrannosaurs, the armoured ankylosaurs, the horned ceratopsians, all of them gone. In geological terms, it happened instantly. One layer of rock contains abundant dinosaur fossils. The next layer contains none. 165 million years of dominance ended in what might have been as little as a few decades. I've spent a lot of time thinking about this transition. I've examined the boundary layer, the thin band of rock that marks the extinction. I've held pieces of it in my hands, and what strikes me most is the precision. The asteroid didn't just happen to hit Earth. It happened to hit at exactly the moment when conditions were already stressed. The Deccan traps in India were erupting. These massive volcanic outpourings had been going on for hundreds of thousands of years, pumping carbon dioxide and sulfur into the atmosphere. The climate was already unstable. The ecosystems were already weakened. The asteroid arrived at the worst possible moment, when the dinosaurs were least able to withstand another blow. And it didn't just happen to hit Earth. It happened to hit one of the worst possible places. The Yucatan bedrock was rich in sulfur and carbon. An impact there released far more climate-altering gases than an impact on granite or basalt would have. If the asteroid had hit the Pacific Ocean, the damage would have been severe but survivable. If it had hit the Canadian Shield, same thing. But it hit the Yucatan, the one place where the impact would cause maximum atmospheric disruption. The timing was perfect. The location was perfect. Perfect for extinction, I mean. 165 million years of surviving everything. Then a single event, arriving at the worst possible moment, hitting the worst possible place, ending everything. That's not normal. That's not random. I'm not saying someone aimed the asteroid. I'm not making a conspiracy claim. But I am saying that the pattern doesn't fit our models. The statistical probability of this sequence, survival of everything, and then instant vulnerability to one perfectly targeted catastrophe is vanishingly small. Something about the dinosaur story doesn't make sense. They shouldn't have been possible in the first place. The conditions required for their existence were too specific. They shouldn't have lasted as long as they did. The stability required for their persistence was too improbable, and they shouldn't have ended the way they did. The precision of their extinction was too perfect. I don't know what to do with this. After 40 years of study, I don't have a framework that makes all the pieces fit. All I can do is tell you what the evidence shows, and the evidence shows impossibility at every turn. Let me tell you where I am right now. I'm sitting in my office, surrounded by dinosaur bones. Some of them are casts, replicas made from molds of original specimens. Some of them are real fossils, 65 million years old, turned to stone, but still holding the shapes of creatures that lived and breathed and walked under an alien sun. There's a triceratops horn on my desk. I use it as a paperweight. Every morning when I sit down to work, I touch it. I run my fingers over the surface, feeling the texture of something that was once alive, that once gored predators, that once caught the light of a younger sun. I've been studying these bones for 4 decades. I thought I would understand them by now. I thought the mysteries would dissolve as I learnt more, as technology improved, as we dug up more specimens and ran more analyses. The opposite has happened. The more I learn, the more impossible the dinosaurs become. The more data I gather, the less sense the story makes. The more questions I answer, the more questions emerge to replace them. When I was young, I thought science was about finding answers. Now, I understand that science is about finding better questions, and the dinosaurs have given me questions that I will never be able to answer. I want to be clear about something. I am not a creationist. I am not arguing that dinosaurs were placed here by a deity. I accept evolution. I accept deep time. I accept the scientific method and the evidence it reveals. But acceptance of the facts is not the same as understanding the facts. I accept that dinosaurs existed. The fossils prove it beyond any reasonable doubt. I accept that they evolved from smaller ancestors. The transitional forms exist. We can trace the lineages. I accept that they were wiped out by an asteroid impact. The evidence is overwhelming. The iridium layer, the shocked quartz, the crater itself buried under the Yucatan. What I cannot accept is that any of this was probable. What I cannot accept is that the standard explanations account for what we see. What I cannot accept is that random chance, operating through known mechanisms, produced this outcome. The standard story goes like this. Random mutations produced variation. Natural selection favored certain variants. Over millions of years, small changes accumulated into large changes. Simple organisms became complex organisms. Small reptiles became giant dinosaurs. The environment changed, the dinosaurs adapted, and when the environment changed too fast, they died. This story is true, but it's incomplete. It's like explaining a symphony by describing how sound waves propagate through air. Technically accurate, missing everything important. The standard story doesn't explain how all the necessary conditions aligned. It doesn't explain why the atmosphere was configured perfectly. It doesn't explain why the continents drifted to optimal positions. It doesn't explain why the climate remained stable for 165 million years. It doesn't explain why catastrophes that should have caused extinctions somehow didn't, until one catastrophe suddenly did. The standard story assumes the stage. It explains what happened on the stage. But it doesn't explain how the stage was built, or why it remained standing for so long, or why it collapsed when it did, and the stage was impossible. Let me summarize what we've discussed across this entire journey. The atmosphere had to have elevated oxygen levels to support giant life. Without high oxygen, the respiratory demands of 80-ton bodies couldn't have been met. But high oxygen should have caused perpetual firestorms. Every lightning strike, every volcanic spark, every bit of friction should have ignited conflagrations that sterilized continents. Somehow, it didn't. For 165 million years, the fires stayed contained. The atmospheric density had to be sufficient for giant pterosaurs to achieve flight. A 500-pound animal with a 36-foot wingspan needs air thick enough to provide lift. But the mechanisms that would increase density, higher pressure, different composition, should have poisoned the animals. Nitrogen narcosis, oxygen toxicity. Pick your poison. Somehow they survived. Somehow they flew. The continents had to drift to positions that created optimal climate conditions. Pangea had to break apart in exactly the right way, at exactly the right rate, creating ocean currents that distributed heat around the globe, creating coastlines that brought rain to continental interiors, creating isolated land masses where unique lineages could evolve. But continental drift is driven by mantle convection, which doesn't know or care about surface conditions. It's hot rock moving around. It has no goals, no preferences, no awareness of what's happening above. Somehow the continents ended up in exactly the right places anyway. The volcanic activity had to release enough carbon dioxide to maintain greenhouse warmth despite a dimmer sun. The sun was about 2% less bright during the Mesozoic. That should have made Earth colder. But volcanic CO2 compensated, trapping just enough heat to keep the planet warm from pole to pole. But volcanic activity is driven by random tectonic processes. There's no thermostat. There's no feedback mechanism that says, release more CO2 because the planet is cooling. Somehow the output was perfectly calibrated anyway. The biological engineering required for giant bodies defies what we understand about evolution. 40-foot necks that required cardiovascular systems of impossible sophistication. 500-pound flying animals that required launch mechanisms no other creature has ever developed. Skeletal structures that shouldn't be achievable through incremental steps because the intermediate stages would be non-functional. Somehow, evolution found paths that shouldn't exist. The reign of the dinosaurs should have been cut short by any number of catastrophes. The Ontong Java eruptions, the opening of the Atlantic, climate fluctuations, sea level changes, the rise of flowering plants. Any of these could have triggered extinction cascades. Somehow, every catastrophe fell just below the extinction threshold. Somehow, the dinosaurs survived everything for 165 million years. And then, at the end, a single catastrophe arrived with perfect timing and perfect precision to wipe them out instantly. An asteroid that could have hit anywhere on the planet happened to hit the one place that would cause maximum atmospheric damage. An asteroid that could have arrived at any time happened to arrive when the dinosaurs were already stressed by the Deccan Trap's eruptions. Every element of the dinosaur story is improbable. Every factor that had to align was unlikely. The compound probability of all of them aligning simultaneously, in sequence, for the duration required, is effectively zero. And yet, here I am, holding a fossil. Here I am, touching a horn that was once attached to a living animal. Here I am, surrounded by the evidence of impossibility. I've talked to mathematicians about this, probability theorists, statisticians who specialize in rare events. I've asked them to calculate the odds. They won't do it. They say the calculation is meaningless because we don't know the probability distributions for most of the relevant factors. They say we can't determine the odds of something happening when we don't understand the mechanisms that would make it happen. They say I'm asking the wrong question. This is true. It's also a dodge. We may not be able to calculate precise numbers, but we can recognize when something is improbable. We can sense when a pattern doesn't fit random chance. We have intuitions about probability that, while not mathematically rigorous, are usually correct. If I flip a coin and it comes up heads 100 times in a row, I don't need to calculate the exact probability to know something is wrong. The probability is 1 in 2 to the 100th power, which is a number so small it might as well be 0. Something other than random chance is at work. The coin is weighted, or the flipper is cheating, or reality itself has glitched. The dinosaurs are like that coin. The pattern of their existence doesn't fit what random chance should produce. Too many heads in a row, too many lucky breaks, too many perfect alignments. I want to tell you something I've never said publicly before. I think the dinosaurs point to something we don't understand about how the universe works. Not something supernatural. I'm not invoking miracles or divine intervention. I'm not suggesting that a creator designed the dinosaurs or that the universe has a plan. I don't know if those things are true, and I'm not qualified to speculate. But something in the deep structure of reality that we haven't discovered yet. Something in the way complex systems behave over long time scales. Something in the relationship between probability and actuality that our current theories don't capture. We know that the universe has laws: physics, chemistry, biology. These laws constrain what can happen. They make some things possible and other things impossible. They create the boundaries within which reality operates. But what if there are laws we haven't discovered? What if there are principles governing how complex systems evolve that we don't yet know? What if there's something about the way life and environment interact over geological time that creates stability where none should exist? What if there's something about the way evolution works at large scales that makes the improbable inevitable? The dinosaurs might be evidence of such principles. Their existence might be pointing to something about how the universe actually operates, as opposed to how we currently think it operates. I'm not claiming to know what these principles are. I'm not proposing a new theory. I'm saying that the evidence suggests our current theories are incomplete. I'm saying that something is missing, because the alternative, that the dinosaurs arose and persisted through pure random chance, doesn't fit the data. It doesn't fit the probability. It doesn't fit the pattern. Here's another way to think about it. Science progresses by finding patterns that seem impossible under current theories. These patterns force us to develop new theories that make them possible. Before Einstein, the precession of Mercury's orbit seemed impossible under Newtonian mechanics. It didn't fit. It was an anomaly. Einstein's general relativity explained it. Before quantum mechanics, the behavior of subatomic particles seemed impossible under classical physics. It didn't fit. It was an anomaly. Quantum mechanics explained it. The dinosaurs are such an anomaly. They shouldn't exist under our current understanding of evolution, probability, and planetary science. They violate too many probabilities, require too many coincidences, persist too long against too many odds. Either we're missing something about how probability works, or we're missing something about how evolution works, or we're missing something about how planetary systems maintain stability, or we're missing something about all of these things simultaneously. Something is missing, and I've spent my career trying to find it. I've failed. 40 years, and I still don't know what we're missing. I still can't explain how the impossible became real, but I believe the answer exists. I believe that someday someone will find it. The fossils demand it. The bones in my office are not lying to me. They existed. Creatures that shouldn't have been possible walked the earth for longer than mammals have even existed. They dominated every continent. They filled every ecological niche. They persisted through catastrophe after catastrophe. That's not a mystery we can ignore. That's not an anomaly we can wave away with talk of random chance and natural selection. Something made these creatures possible. Something maintained the conditions they needed. Something kept the stage standing for 165 million years. Let me tell you what keeps me going. Every year, we find new fossils, new species, new evidence of how dinosaurs lived and died and interacted with their world. And every year, the picture gets stranger. Every new discovery adds to the impossibility rather than resolving it. We found dinosaurs with feathers. That added a new layer of biological complexity that had to evolve. Feathers are incredibly sophisticated structures. They require genetic programs of enormous complexity. They had to evolve from scales through intermediate stages that we still don't fully understand. We found dinosaurs at the poles. That expanded the environmental range they tolerated. Dinosaurs in Antarctica, dinosaurs in the Arctic, animals that were supposedly cold-blooded, living in regions with months of darkness and freezing temperatures. We found dinosaurs in ecological niches we didn't think they occupied. Swimming dinosaurs, burrowing dinosaurs, dinosaurs that apparently ate mammals. Dinosaurs that apparently hunted in packs with sophisticated strategies. That increased the diversity we have to explain. We found soft tissue preserved in dinosaur bones, blood vessels, cells, possibly even proteins. Material that shouldn't have survived 65 million years of fossilization. That added mysteries to mysteries. The more we learn, the more impossible they become. A scientist should be troubled by this. A scientist should want explanations. A scientist should be bothered when the evidence doesn't fit the theory. I am troubled. I am bothered. I want explanations. But I've also learned to sit with the mystery, to accept that some questions don't have answers yet, to trust that the universe will eventually reveal its secrets if we keep looking, keep digging, keep asking. The dinosaurs are impossible, but they existed. That contradiction is not a failure of science. It's an invitation. It's the universe telling us that we don't know as much as we think we do. It's reality demanding that we dig deeper, think harder, question more. I'm 67 years old. I've spent 40 years studying creatures that shouldn't exist. I probably won't live to see the mystery solved, but someone will. Someday, someone will find the missing piece. Someone will develop the theory that makes the impossible possible. Someone will explain how the stage was built, why it remained standing, why it collapsed when it did. Until then, all I can do is what I've always done. Look at the bones. Touch the horn on my desk. Marvel at the existence of creatures that defied every probability. Keep asking how. Keep asking why. Because the dinosaurs were impossible. And impossibility is the beginning of knowledge, not the end. The evidence is in front of you now. The fossils are real. The measurements are accurate. The timeline is established. The improbabilities are stacked higher than any statistics can justify. Now you have to decide what you believe. Do you believe that random chance produced an impossible world and maintained it for 165 million years? Do you believe that all the factors we've discussed, atmosphere, climate, continental position, biological engineering, survival through catastrophe, precision extinction, just happen to align through pure luck? Or do you believe, as I do, that something else is going on, something we don't understand yet, something that makes the impossible possible, something woven into the fabric of reality that we haven't learned to see? I can't answer that question for you. I can only show you the evidence and tell you what I've concluded from a lifetime of study. The dinosaurs existed. They shouldn't have. That's the mystery. And that mystery is more profound, more disturbing, and more beautiful than any story I could invent. Look at the moon tonight. Think about how it looked 65 million years ago, hanging over a world filled with creatures that defied physics and probability, creatures that stood taller than buildings, creatures that flew like aircraft, creatures that ruled every corner of a planet perfectly configured to support them. Think about the impossibility of their existence, and then think about what that implies for everything else we believe we understand. The universe is stranger than we know. The dinosaurs are proof. And somewhere out there, waiting to be discovered, is the truth that will finally explain how the impossible became real. I won't find it, but maybe you will.